So, oh, hi. Let's see.
Oh. Sorry.
Um, can you hear me? Oh, perfect.
And you're using the HDMI1?
All right, great.
Is that us?
I have no idea what's going on. Oh, I'm connected. I see, yes.
The sound's coming out of the projector.
All right.
Track 2?
One.
1, 2, 2. Track 2.
Okay, thank you. Yeah, thank you. All right. We had 2 people, we lost. Well, maybe it was you guys. All right, anyhow. Yeah, so I should do a little bit of duality, and then we'll start numerics finally. So yeah, just to remind you, we started the minimization problem, and you have some constraints, and you put them all in the Lagrangian dual, and this is a miraculous function because regardless of the original problem, this is always concave because it's linear in lambda and mu. So if you take derivative in lambda and mu twice, it's dead. Yeah. So this is always concave, so it has a solution. And we talked about a little bit that you always have this beautiful lower bound for your minimization. And when they're not equal, it's said you have a duality gap. Okay. So we have maximum of G lambda over lambda is less or equal than infimum or minimum of F. Okay. strong duality can fail. We talked about this. So this is a problem of e to the minus x. So it goes like this. And you can see from the picture that the minimizer is 0. Right? So minimum of e to the minus x is 0. But if you compute the dual function, so the dual function is the function itself plus lambda of the constraint. And we talked about this last time. And now I don't remember. So what did we say? It's 1. I'll do it again. So take lambda to be non-negative, then take minimizer. So take y to plus infinity. This guy is 0. So you're left with infimum of e to the minus x, which is 0. Right? Yeah. And then take lambda to be strictly negative. Then you can take again y to plus infinity. And then you will get minus infinity. Okay? All right, anyhow. But the point is the minimizer of this guy is 1. So this is equal to 1. Because this constraint is the same as saying x is 0. Okay. The only way you can have x squared over y to be non-negative and y is positive is when x is identical to 0. So the physical set is only 1 point. So you get e to the minus x is 1. Okay? Yet from here you get that the maximum of g lambda is 0. Okay? So you get the duality gap. That 1, so the infimum, so minimum of e to the minus x in the constraints, minus maximum of g lambda is equal to 1 minus 0. So you don't have strong duality. Okay? So strong duality is not always true. Okay? One way you can have strong duality is like you do in the midterm, you just check through all those guys. And if you have them, you have strong duality. So I want to do it carefully this time. So the claim is if you have KKT, then you have strong duality. Okay. So this is the maximum of G lambda. Right. So P star is equal to T star, strong duality. All right. So let's prove that again. Because it was Russian. So one of the KKT conditions is that the Lagrangian is 0. Okay. So we have a special point. So again, KKT. This is one of the conditions. Right? So one of them, so you have a 0. But you also, one of the KKT conditions is that you have a positive definite. Okay, so you put the two together and you have that this guy is a minimizer, right? Is that okay? So Laplace square of lambda is this guy plus this gives you this. That's from second week. Okay? Okay. So, so that's the minimizer. But these are also feasible conditions, right? So this guy is 0, and this guy is 0 because we only kept active, right? GI equals 0. So again, let me remind you, when GI is inactive, what is mu I equal to? 0. So it doesn't even show up here. Okay, so that's why you get 0 for 0. All right. Okay. Right. So this is the minimizer, and this guy is equal to the maximum of G lambda. Okay. So that's why that. All right. Good. Questions? All right. So in other words, when you want to check the strong duality, let's check KKT. Let's go through each of them, and you will have strong duality. So let's do some examples. So these are from the convex optimization book. So here we just have simple log problem, and AI are fixed parameters. I have some pictures here. Yeah, where's the picture? Picture. We'll talk about it. Yeah, we'll talk about it. So anyway, so this is the original problem, and I have to find the dual. And what do? You take the function, so that's the function. You take one of the constraints, you multiply it by lambda, and you also take the non-negativity. Sometimes you have to do it, sometimes you don't. Here it turns out that you need it. Okay? I'll let you know when you don't. All right. So we go through the KKT. Right, so let's start with this one. I'll talk about one. So you need stationarity. So you compute that. So what was it? So let me do it with you. So minus log plus 1x plus mu. Okay. So all right, so we're going to take gradient. This is L. We're going to take its gradient. So, you can. So, what's the gradient of the first guy? First. With the minus, right? So, let me put the minus. So, A1 plus X1. And what about the second guy? So this is the dot product. So summation. What do I put in the? Yeah, so you just put 1. Might as well write it as 1 vector. And what about the last one? No. Huh? Yeah, it will be mu1 all the way to mu1. So you have this. You have the system. But you're lucky, you got decoupled, so you can solve in X. So you will start active, inactive. So first of all, say it's active. That means Xi is 0. And that tells you something about the AI, which we're going to use soon. But anyway, so this is one constraint. What else? And then second case, suppose it's inactive, then I need to find the xi. So when it's inactive, yeah, no. So when it's inactive, this guy is 0. So you just solve for it. Okay, so here, let me do it in case you got lost. So we have AI plus xi plus lambda mu y, but I know mu y is negative, so I upper bound. Right? Yeah, and then actually I know it's 0, so why am I doing this? So this is equal to mu, which is bigger than 0. So then you have lambda is bigger than AI plus x. Okay? Because it's active, so GI is 0, which is xi is 0. That's why I needed to write that. You can do it. You can always add them, but usually it's more work. You can still find the minimizer without adding the non-negative questions. Okay, so you put the two together, and this is your minimizer. So it's not a clean expression, but that's the best for you. So the minimizer is attained at these values. So you plug it in back. Right, yeah, so that's a short way to write it. Right, now I can even find it. Okay, let's do that too. So this is one of my constraints and I need feasibility. So yeah, you just plug it in and you get this, but you can't always solve from there, unless you know what AI. Let me just give you what G lambda is too. So since we found the minimizer, yeah, so this guy is the G lambda mu. And yeah, it's not a nice expression. You can't even, it will be disgusting. And you don't have to do it. So G, anyways. So yeah, so right, I should give you the dual problem. So the dual problem is the dual problem would be take the maximum for lambda and mu and plug in the in L, plug in the minimizer x star. Plug in this guy. Oh yeah, and given the constraint maximum 1 over lambda minus AI 0 to 1. Okay. Okay. So that's the dual problem of that other one. I mean, it's disgusting, but I just want to write it down. Okay. All right. What else? So I want to talk about support vectors. This is more relevant to statistics. Yeah, you say this unless you haven't seen it already. It's one of the basic tools in machine learning. So here's some nice pictures, and then you solve it. So you have 2 data points. I want the picture, yeah. So you have two classes of data points, black and white, cats and dogs. Okay. And then this could be images, right? And you pixelate them. So you have some reference. So you have two classes of points. And then you start with a new point x star. Yeah, so you have a new data point. And you want to classify it. You want to know whether it falls in this class or in that class. Okay? But how do you do that mathematically? Right? A computer doesn't know cats and dogs. It just knows points. So your job is to find a line that will separate the two classes of cats and dogs. Right? So the optimization problem we're going to solve is to find this line. Okay? So I think I have some bad lines. What's a bad one? It's not here. I had a nice picture with bad lines. So here's, oh yeah, this is the picture. So this is a bad line, right? So this guy here is a bad line, and this guy here is a bad line, right? Huh? Oh, no, yeah, of course you can do more general, but support, I mean, yes, absolutely. You can have, you can even have what's called the most used one is Gaussian kernel. So it goes like, does something like this. But I don't know, this is like the baby, like the most standard thing. So yeah, this is a bad line because on the left and on the right, you have cats. You don't want that. And same thing. Actually, this is a good line. So this is a bad line. Let me draw so this is bad. And this is good, right? Because it has left and right cats and dogs. Yeah? Does that make sense? So let's find this. So we're going to turn this into our optimization problem. So if you go to any blog on support vector machine, they solve the optimization. So I'm going to pull that, because now you have the background. You can understand what's going on with the back, instead of just putting it on. All right, so what's the mathematics? So if I give you a line given by WXB, right? This is in higher dimensions. Any line is given in this form, where you fix W and B, okay? All right, then so the distance from this line, the minimum, so this is H, is given by this element over here. Okay. So I think I covered it. I don't, that's fine. I'll let you do it. I don't know, it wasn't that one. What was it saying? I don't know what I think. Can we guess it? How would you find it? So you have Z minus WX plus B infinity over X, such that, no. It's like this. W minus X, so that WX plus B is 0. Then I think just plug it in. So you have infinity of W equal to minus, let's pretend this is 1D, okay? We'll think about the other one later. So this is minus B plus over W. Too many W's, it's Z. Like this. And then you cross multiply. Okay, so you have WZ plus B over W. Okay? This is in 1D. Do you understand? Have you lost? What? Tell me. Is that okay? Well, if you're staring at it, it's not clear. So I do it again? Can you tell me if I should do it again? Okay, good. Thank you. Like, I don't know, I
if you could do it again, that'd be nice.
The question is find the distance of z to x, where the points x satisfy wx plus b equals 0. Okay? Is that okay? Because we want to find the minimum, we want to find the x that's closest to it. Yeah. Is that okay? Can you what? Well, now I'm doing 1D. I know this is dot product. There's a lot of stuff here. I'm not doing the full thing. No. I'm just doing like 1D just to tell you how the, yeah. Okay, otherwise it's actually another optimization problem. So I don't want to do that. It's too much. Like, yeah, exactly. So if you want to get the full thing, you have to take gradients. And okay, so, but I'm just saying in 1D, where everybody, these guys are real numbers. Then you just plug it in, what x is, and you get wz plus b over w. Okay. Okay. All right. Good. Yeah, the full thing requires optimization. Yeah. All right. Yeah, that's right. That's right. Yes. Yeah, okay, thank you. All right. So this is the distance, and let's do the optimization problem. So again, the goal is to have some points labeled by 1, 1, 1, minus 1, minus 1, minus 1. Okay, these are the labels. Okay. All right, and then you want to do the following. So you have, anyways, so you have these labels. And these are the xi, so x1, x2, x3, x4. And these points xi come with labels, yi. Okay? I should use a different notation because, no, it's okay. So this is a tuple, right? So you have x1, y1 is a tuple, okay? And x, the x guy is some point in Rn, and the y guy is either a 1 or minus 1. Okay, so they come with labels. Is that okay? Do you understand? Okay. Oh, do it. Yuling? This is not the point x41. That's why I hate this notation. This is the point x4 labeled as 1. Yeah, we can come back to that at the end. Yeah, B is a vector, but I did it in 1D. Yeah, I told you, the full thing requires optimization. Please, yes. All right, good. Anyways, so you have points, you have labels, and the claim is that this problem, once you solve it, it will separate. Okay, so let me give you some intuition. I think it's here, right? It's not. Let me give you the intuition. So, what is it? Yeah, so let's do the y1. So y1, let's say it's 1, and then you want wx1 plus b to be bigger than 1. I mean, the 1 is irrelevant. We just want them to be parallel. Right. So let me draw the line. So this domain, how should I do it? So this is the line wx1 plus b, and the guys plus 1 are over here. So this is the plus, bigger or equal than 1, and this is the less or equal than 1. Right. Let me say, you understand? So maybe I'll do it this way. I'll call it this -1, and I'll say this is the bigger or equal than 0, and the less or equal than 0. Okay. Do you understand? Is that okay? All right, so this is your constraint. You want, if you have a label that's positive, that you're on the above the line, and if you have a label that's negative, you want to be below the line. Anyway. Okay. And the intuition about this minimization of W, this is just the slope. Okay, so let me give you the intuition for W. Why do we minimize over W? So I'll do it here. So this is, again, I'm doing 1 because it's too much. So what happens as W goes to 0? What happens to the line? It gets flattened, right? So when x is 0, it hits at B. And so, okay, when x is 0, what do I want to say? Call this y, not y, this is bad. Call it f of x. At x equals 0, your b, and then what do I want to say? And this guy is minus b over w. So it goes like this. And the slope is w. So as w decays, it gets flattened, and as w grows, it goes up. Right? So you're covering the entire domain. Right? So your line goes up and down. Okay? That way you will eventually find some separation. The full problem, oh yeah, the dual problem, let's talk about that. Let's find the dual problem together. So yes, so the dual function, the Lagrangian is W lambda, just actually just mu. So you have your function of W squared. And there shouldn't be there's no I. Okay. And then mu of 1 minus y. Oh, I see, here. It's a summation. Is that okay? So this guy is in Rn. This guy is in Rn. Yeah, I don't know why I put I there. There's no I. There's no I over here. I mean, sorry, what? No, I mean, it's not, I could have put maximum. Actually, maximum might throw you off too far. Because like if you, so what do you want? You see here, if I take W to be big, this could be true without constraining me to be. You see, they have to work opposite to each other. So so take take W I want to be 1 and have these guys be positive. Then as you take W up, this becomes trivial. Yeah, but then, yes, but yeah, let's do this one. This one is more interesting. So take this, but then you want it to be bigger than this. So let's see. So W psi needs to be non-negative, needs to be negative. So let me take it to be 1D. So we have less than minus B psi. And then it needs to be actually, you know what? You might be right. I don't think it matters whether we take max or min because yeah, so it doesn't matter. Like as long this constraint works both ways. It doesn't allow you to go too far this way, and then it doesn't allow you to go. So yeah, it doesn't matter. It's symmetric. Yes. Well, this is a vector, right? W, I know WY. This is a vector. This W is a vector. I mean, are you talking about 1D or what are you talking about? Because if you take W to be too small and W and YI is positive, then you risk being less than 1. So you cannot put like W equals 0. Is that okay? You mean, is that okay? Okay, well, we can talk about it at the end. All right. Okay, anyway, so this is the dual function. And yeah, let me do the Lagrangian. So the gradient will be W, and then it will be mu minus mu1, y1, x1, minus mu n, yn, xn. Okay, so then you just solve it and you got your minimizer. So W is equal to mu1, y1, mu1, yn, xn. Okay, so that's the minimizer for this problem. And then what do you do? What's the dual problem? Well, you take just the maximum. So you take maximum over mu of lambda evaluated at W star. Okay, so that's the dual problem. Okay. Questions? You may talk at that. I don't want to like. This is a very cool material. Yeah, this is very cool stuff. That shows up. They even, I was reading the blog, they even have an advanced version if you want to check it out. So I keep writing WI. I don't know why I do it. I don't know why I don't have to write it. So here you minimize over both the slope and the intercept, and also what's called margin. So this margin means, let me do it here. It tells you how close you want your line to be to the points. So let's say I have 3 cats, 1 dog, and if I want my line to be very close to the dog, or whatever, I take gamma to be very close to 1. Okay? So these are called margins, and it tells you how close you want the line to be to one of your points. So you have more freedom. And this is the problem that the action study. The one I gave you before is like a basic version. This is the full thing because you have freedom over the intercept and the slope and the margins. Okay. Okay. So shall I do the? I think you can. I mean, I'll do it to you. It's not hard. This is more disgusting because you have more variables. You have W, P, and gamma. So it will be a longer thing. Oh yeah. Okay. All right. Good. Can I go on? You have a question? Can let me know. Zoom people, if you have questions. All right. So for the next 3 weeks, we're gonna do numerics. That's a part of the course. I don't expect you to do MATLAB, but it would be nice if you can understand some of the code we use. So you won't be tested on this code, but you will be tested on the methods and the theorems. All right. Let's go. We spent about a month talking about existence and uniqueness with first and order second condition. But often we do not have closed forms for the minimizers. I mean, this is a landscape from a neural net, and you can see they're discussing. So there's absolutely no hope that you can write X star as some formula. So we can forget that. Also, you have another problem, again, in neural nets. You have what's called a matrix of weights. And often this go into the like 60,000 size. So when you start inverting these matrices, you're in trouble. Okay, so trying to like find W inverse gets very, very costly. Okay. So that's another reason why solving it exactly is too expensive, and numerics tend to be cheaper. Okay. And finally, again, for neural nets, let me zoom in. That's a cool thing that you might hear about. So they did this recently, about a year ago. They took a data set of dark matter. You can look it up. Oh no, you're an astronomy guy. Yeah. Astronomy, right? Okay, so they took data set from dark matter and they put some traits about it, like density and velocity and stuff. And they used neural nets to find connections. So they found these amazing formulas for neural nets that relate various features of dark matter. But again, this is disgusting. This is some crazy recurrence relations that you cannot solve analytically. Okay, so again, you have to come back and do numerical methods to solve for these constants. Okay, and that happens in physics all the time. your answers are things like, sine t over t, right? Which have no exact answers, or the Gaussian, it has no exact answer, right? There's no closed form for these guys, right? Yeah. So anyway, so that's why we care about numerics. Okay. All right, that's the motivation. All right, Newton's method in 1D. We'll talk about this a bit and we'll take a break. So we start with the function. Unimodal means it has a single minimum. A picture. So unimodal means it does stuff like this. So, but it doesn't, okay. I have to draw it in a crazy way. So there's no local minimum. How do I do it? What do we do with it? Okay, so you have no local minimum. It only has one local minimum. Okay, not global minimum, local minimum. These other points are not local minimum because you are here. You're flat. Here you go up, and here you drop, but here you're flat. Okay, so not strict local minimum. Okay. So that's unimodal, and you want to find x star. So what do? This is a nice function from mean value theorem. Okay, so first derivative, second derivative. And what we talked about on first derivative is that you want this guy to be 0, right? That's the minimum measure. So yeah, you take your derivatives. So let me give you the algorithm before the break. So you take a derivative in x, or x1, and yeah, so you're left with the first guy is dead, right? So again, what was qx was f of x 0, f prime x minus x naught, and then f double prime x minus x naught squared. Okay, so if you take d dx of q and plug in the next step, you get this equation, and you solve for it for x1. Okay, and what does it say? It says that x1 is given by this point. Now, do we have that f of x1, that x1 is the minimizer? Is it? For f? Yeah, but this is q of x is not f of x, right? So x1 is a minimizer for q of x, right? You understand? So no, this guy, yes. Now, if you add more terms, right? Because this is the second order approximation, right? So if you have more terms, then yes, right? Because for example, f of x would be e to the x, which is equal to a summation of xk, k factorial. So you have infinitely many polynomial terms, but this only goes up to 2. So of course it's not f, right? No? You mean? What? No, like what I'm saying is, let's do it carefully. So we want to find minimizer of f of x. The most reasonable approach is you just take its derivative and you set it to 0, okay? That's what we did up to now, okay? But the answer to this could be very complicated. Okay, it could be some crazy integral. I don't know. Okay? Right? I don't know. Something crazy. Something not closed. So what we do is we say, okay, forget that and approximate it by Q. Okay? So you have F, double prime, double prime. Okay, I mean, you know it, but some people might not remember it. There's a result that says that the Taylor approximation of F, so probably that's why you're lost. Minus F of X not goes to 0. Okay, that's all they're using. They're using that the Taylor approximation converges to the, this is F of X, right? Converges to the value F of X. Okay, this is called Taylor approximation. Okay, so that's what they're using. They're saying, I don't want to solve the original stationary problem, so let me solve it up to second order. Okay, and it turns out to be good enough, which is amazing. You would think that you need to take n to be really big, but it just take n equal 2. Okay, right? Okay, so let's take a break. Zoom, Daniel, any questions? I didn't hear you guys. Were you using the mic? That's fine. Today. Are you sure, Daniel? Are you okay? Like, usually you have questions.
Yeah, I'm fine.
Okay. Oh, I see. Andrew is here. There's a lot of people. Yeah, you guys can participate. You know, like, I would love to hear your input. If you want me to go over something from before, just let me know.
Hi, Prof.
Yes.
Will this week's quiz be on KKT conditions and duality?
The quiz 6 problems were posted in the announcement, right?
Pardon?
Like the quiz 6 problems were posted.
Like 2 weeks ago, right? When you posted the midterm?
I will take it from there, like some notification from there.
Okay.
So what? Is my pixel on? What, does it have to be differentiable or something? No, why not? How will I apply? Let's see. Maybe you're right. I think you're right. Because f prime will be, right, so f double prime will be infinite. I mean, it would be zero, so the ratio will be infinite, yes. I mean, it just says that you're not allowed to start from there. It doesn't say, yeah. I mean, that's the definition of being model. I don't know. It doesn't say that f prime has to be. I want to, okay, I mean, how should I draw this? I want to draw that it has only one local min, but it's not convex. So it's not the global min. Because either you go this way, which is local min, but then you have more than one local min. Well, I think you're right. I like this. Yeah, because then it's not convex. Maybe something like. But then, yeah, okay, I like this. Yeah, it's nice. So only one. Yeah. Yes, that's right. No, the distance is right. Oh, because you're saying B could be, no, B is not a vector. B is a number. Yeah, exactly. So I think actually I was right. This is that. So it's the R component. So W is equal to W1 to Wn. So then it should be like minimum over W and I. It should be something like this. Because I agree. Otherwise, what? You can take the sum, or you, yeah, I mean, it doesn't matter. I mean, fine. Yeah, yeah. Fine. It's not, the vector is not, the planning functionality. So, I mean, of course it is. You can look at the wall, I mean, there's some. W could be 1, 1, 1, 1, 1, and then another choice could be 1 with all zeros. The norm went down, but this is the total. The point is that it changes the plane. You have to figure out that it changes the plane. Yeah, right. So basically, yeah, I agree with you. I got something what I got. But this is not so like you have to take some action, right? You talk about sales, like I mean, I would do the And you take the smallest one that will Yeah. I wish I had some simulation. I mean, well, if B is positive, no, because some of the labels could be negative. No, like you said, big W could be 0. All right, let's go. So, Newton's method. Again, the basis of this result, known since Newton's time, in the 1600s, is that if you keep adding more terms, like f cubed and fn stuff, this guys will converge to f of x. Okay? So that was the initial motivation to say, okay, I cannot solve f prime of x equals 0. This is hard. So let me solve the approximation of it. Let me solve instead q prime of x equals 0. Okay, because this is a polynomial in x. And I can solve. Yeah, I can take the derivatives and set them to 0. So I do that. And if you do that, you get Newton's method. You get q prime of x. Too many words here. So q prime, you set it to 0. The first constant that is dead. This is times 1. And there was a half, so 2 cancel out. And then you solve for x1. And x1 will be the next initial point. Okay. Yeah, let me do this and then we'll do some. So you start with some starting points. And the way you take your next step is you keep solving this q guy. So, you like we did before. So we solved 0 equal to q prime xn plus 1. And then this will give you xn plus 1 to be xn minus this stuff. Okay. So that's how the method works. And we will prove convergence because it seems very abstract. So we'll use a mean value theorem and stuff like that. And we will also prove convergence of that sequence. And yeah, so let's talk about picture. All right, so you start with x naught. This is your first guess. Usually this guess is done randomly. Okay, like in numerics, because we don't know what's a good guess, because the landscape could be very complicated. And then, yeah, so x1 was what? It was the x0 minus f prime of x0, and then f double prime x0. So if I rearrange this with this notation g, so what is it? So let's see. So you have g of x0 is equal to g prime of x0 times x0 plus x1. Right? Now this is a line, right? This is y, and this is the slope. Okay, so this is the slope g prime. Okay, so this is the slope, and the intercept is x1. So this is the intercept. So it hits it at some point. Let me clean this up. So I have an intercept and that's the line. And then you start again. So you hit it, and then you have a new slope given by now will be g prime of x1. Okay, that's the new slope. And you keep going. I want to do numerics. Do I have it? I'll do the descent. Okay, so let's show that this sequence converges. So we show that right, okay, so xn are the steps. So xn plus 1 was xn minus f prime of xn over f double prime of xn. And we will show that this guy converges. So what does that say? It says that as you take n to infinity, the next step, xn plus 1 minus the minimizer, is less than some c, xn minus x star p. Okay, and why is that cool? Because if you keep reiterating this, you get some c to the n and x0 minus x star to the p. And okay, now if c is less than 1, okay, so this constant is called c. Okay, that's the order of convergence. Constant over here. Okay. And if c is less than 1, this guy goes to 0, as n goes to infinity. Okay, so that means that this guy over here goes to 0. So indeed you get xn goes to xn plus 1 goes to x star. Okay, so let me repeat. I mean, I'm going to prove it. I just give you some intuition. So this is called the order of convergence, is constant. this ratio of limits. So try to remember ratio test. This is just ratio test from first year. And the proof is the same actually. This is like first year. So this guy, this implies this. There's some error. I'm not going to put the error. Doesn't matter. And then if you keep reiterating, so recursion, you end up with the initial point times this order. So note how you get punished by taking a x0 away. So far, extra. So you will never escape this problem. You always keep coming back. But your choice needs to be very good. Okay. All right, good. So now let's, what I wrote, make it rigorous. Example. So let's compute this order. Again, this is first year example that I took. I'm just going to do ratio test. So take the sequence xn rn. By the way, the function xn looks like this. So it goes like your 0 at 0 equal like this. Oh, yeah, you should know this. Yes. So this is x1 and this guy is xn. Okay, so as xn goes to infinity, you go to 0 when x is less than 1, and you go to 1 when x is 1. Okay. All right. That's why we need to take strictly less than 1 because you don't have convergence. So again, that tells you that if your initial point is 1, you're dead in the water. You cannot do that. Okay. Let's compute the order. So I'll do it here with you. So this is Rn plus 1 minus 0, and then Rn minus 0. And this just leaves you with R, right? And this is a finite number. So here we can take P to be 1, and in the discussion above, we take C to be R. Okay? So that would be your order of convergence, meaning how fast you go to your limit, x star is 0. I should do one more complicated question. So let me do one more. Take xn to be whatever you like. I don't know, 10. Then same thing, right? You will just have xn minus 10 will be Rn. So that would be the order of convergence. Is that okay? It's not very complicated. Oops. All right. Oh, right. And then this value is short. So let me prove it. So, I mean, this is a nice homework. Put some stuff like this. So that's just first year calculus. So now, why is it sharp? So why is sharp? So again, let's do this together. You have Rn plus 1 minus 0 over Rn minus 0 to the P. So that leaves you with Rn plus 1 over Rpn, which is the thing I wrote over here. Okay, so let me do it. So you have R, and then you have N minus Pn. So you have R, N, 1 minus P. So you have R, fine, P minus 1. Okay? Now, if P is not 1, but bigger than 1, let's say 1 plus epsilon, then what do you have? you have r to the 1 epsilon n. Yeah. So then this is r over epsilon n, and this goes to what? R is less than 1. And epsilon is fixed. P is equal to 1 plus epsilon. So what's the limit? Yeah, it goes to infinity. So you're not allowed to take P equal to 1 plus epsilon. Yeah, this is M to infinity. Because r epsilon to the n, this guy is less than 1, it goes to 0. So 1 over that goes to 1 over 0. Okay, good. So that's why it's sharp. So P needs to be 1. Okay? So if they ask you for sharpness, that's what they want you to show. All right, good. All right, now let's prove convergence of I got an infinite loop. Let me pause. Oh my God. Stop. It's crazy. I hope my computer won't die. Like the order. So you need P so that xn minus the minimizer over this one to the P is finite. So for P equal 1, you're good. But when we put P equal to 1 plus epsilon, we're not good. It blew up. You're not allowed to be, you're not allowed to put P equals. Can you speak up? Yeah, but you understand, like I'm not allowed to take a little bit above it. Yeah. So yeah, this is the sharp. Okay. Let's finally prove that this is convergent, this algorithm. So, like Yumi said, you have to be careful with your derivatives. So you're not allowed to have 0 derivative. So I should remind you, because G is equal to F prime, and G double prime, sorry, and G prime is equal to F double prime. I don't want to keep writing triple prime, because this is triple prime. It's too much, too many dashes. But anyways, this condition says that F double prime is not allowed to be very flat. So you can have, so this is saying F double prime being not 0. So you're either convex locally or concave. You can just be like this. Okay. So given these 2 conditions, we can use our Newton's method. So again, what is Newton's method? Just to drill it in your head, is G xn over G prime xn, which is F prime of xn over F double prime xn. Okay. So in order to do Newton's method, I need the thing I divide by to be not zero. All right, that's all. There's nothing. And we're going to show that P is at least 2. Questions? All right, let's start. So F is C3, and F being C3 means that F prime, F double prime, and F triple prime are all continuous. Okay? So the same is true for G prime, which is the F double prime, and this is the triple prime. So I'm going to prove to you that just by continuity, you have this bound. Okay? That's what I will. Okay. We know that the G prime is not 0. Okay. So the picture is, here's your graph. This is X star. And we know that the second derivative, which I think we called it the slope, it was, so G prime is not 0. So, yeah. So we know G prime is not 0 in the neighborhood of it. I mean, at the point. We know it's not 0 at the point. Now, here's what happens with epsilon delta. Right? So, suppose G prime of X naught is bigger than epsilon. Then take, by continuity, take delta so that G of X minus G prime of X naught is less than epsilon over 2. Okay? So the picture is you have this, and you have X, which is delta close. So from this, you get that G prime of X is bigger than G prime of X naught or star plus epsilon over 2, which is bigger than epsilon minus this. Okay. Epsilon delta is fun. So by continuity, you get G prime will be, you get that G prime of X will be bigger than this epsilon over 2 that I talked about, that they call it alpha. Okay. This is in the book. They never use epsilon delta, they just say continuity. So there's a lot of meat behind continuity. And fine, you do the same. So for G double prime, again, you use continuity. Yeah, so, oh, for this one, you use something else. Here's what you use. You use what is called extreme value theorem. Okay, so in the closed neighborhood, B delta of X star, the G double prime of X is bounded by 1 over alpha. Okay. So extreme value theorem says that you give me any compact region, I can always find the max and the min. Right? Is that okay? So this is the max. You mean? No? Okay. So that's how they get these two numbers, these two bounds. So I should add some intuition here. Like, yeah, let me go back to what you said. So suppose you have your minimizer and you have a flat region over here. Then here you have the G prime is 0. It's not bigger than some alpha. Okay? So that means you're stuck. You cannot jump to the minimizer. Okay? So Newton's method fails if that happens, because you will have xn plus 1 is equal to xn minus G prime of xn over G double prime. But in this guy is 0. So you're stuck. You're not making progress. You understand? So flat regions are bad. Newton's method fails. Okay, good. And the other bound you need it so that we'll use it next for convergence. Yeah. So this is our algorithm. And here I used that G of x star is 0. Okay, so it's a stationary point. No questions? Cross multiply. So I multiply it like this. Okay. And now we're back to first week material. This is, I say over here, this looks like the second order Taylor approximation, right? So you have, remember, it was f prime plus a half f double prime plus O of x minus x star squared, right? This is a second order approximation, right? You have a correction term that is of second order. Okay, good. So you plug that in. You plug it in. So you have this plus some error. You write the error. So you have O of xn minus x star squared over G prime of xn. And now you use your bounds. The top guy is less than 1 over alpha. So you have 1 over alpha. And the bottom guy was was bigger than 1 over alpha. So bigger than alpha, yeah. That's how you get alpha squared. Okay. So why am I doing this? Because I want to give you the order. Hopefully you remember that the order of convergence is given by the ratio of these two. Some P. So now it's just calculations, but even from here I'm done. But let me do it. So yeah, so this was proved for every n, starting from 0. And I want to give you the order. So I set rho to just be, so I split this. So rho, this guy, and what do I want to say? Yeah, so I mean, this is a big issue, right? So again, that's another point to talk about. So let me do this with you. So we have this, then we proved from before, about, I don't know why I'm doing this. And we just proved from above that this is equal to rho. So we got that this guy squared is less than the square root of these two. That's how you get rho squared like this. And then you get rho squared. All right. Where we use that x naught is close to the minimizer. So yeah, there's a lot of problems with this method, right? I mean, this being close is one of the downsides of inconsistency. That's why we often use gradient descent. So this is the biggest downside. Even the proof doesn't work unless you have closeness. So you keep doing this and you get this guy. And let me add a word here called fixed point and contraction. So you've probably seen this. Oh, you said this. So here we show that this sequence goes to 0. Why? Because this is of the form C rho n, where rho is less than 1. And so as we talked about before, since it's less than 1, it goes to 0. Okay? And again, you see x0 shows up, the initial point. If x0 is bad, the convergence is bad. Okay. So this method doesn't always converge. That's very important. All right. So I proved to you that that the limit of this, which is called the convergence rate, C, is bounded by this 2 alpha, which was used to classify flatness. So remember, G prime or F double prime is bigger than alpha at X star, and the triple prime was not too big. Okay. And this P is not sharp, so meaning it could be plus. So it could be 2 plus epsilon. All right. This is 1D. The world is not 1D. So let's talk about higher dimensions. How do you do Newton's method in higher dimensions? Again, you need the third derivative. That's because in the Taylor approximation, your error depends on the third derivative. So that's why you keep seeing this C3. And it's because in Taylor, we have error depending on the triple derivative. That's the problem always. Local minimum, convexity, that was our first 2 weeks video, first 3 weeks. You need positive definite Hessian and local minimum. So meaning stationarity. Yeah. Then this is the Newton's method, okay? So this is the multidimensional version of it. I cannot divide by Hessian, that makes no sense. But it does make sense to take its inverse, right? So as an exercise, put n equal 1 to rederive the formula xn is equal to this. Okay? So, So this is very complicated, right? This is a matrix. And it's times its own gradient. So this is a vector. So these guys are all vectors. All right. Now let's talk about the. All right. So this is a very ugly function. But if you just draw it, it looks like this. Maybe a little bit curved. Let me do it a little bit like this. Okay. So we know it's minimizer than 0 from the picture, but Newton's method is not so good. So yeah, so I have to take derivatives, right? So I take first derivative, second derivative, and right away you get that f double prime. So let me do the derivatives with you. So let's see. So we have x times square root of x, right? So could do it like this. And if you take derivative of this, you get the square root of x. Okay. Let me do it with you because it's easier. So let's do the x positive case. So you have x and then you have square root x. Now let me do 3/2. Why am I killing myself? So take derivative of this, and you have 3/2. And then you have a half, right? Yeah, just split cases is a lot easier. All right, so these are the derivatives, and right away you see we have a problem. If you take the second derivative, you have 1 over square root x, and this guy diverges. Okay, so if you remember in the Newton's method, we asked for f double prime of x star to be bounded, right? But now 1 over of 0 is infinity. So that's why Newton's method will fail. But let's prove it. Let's talk about it. So I take my initial guess to be a very small epsilon. So again, this is my function. This is my minimizer. And this is my initial guess. Okay, so I start my method from here. Let me find the first point. So the first point is this guy minus this, and I will compute this with you. So f prime of epsilon is equal to square root epsilon, and f double prime of epsilon is equal to a half, and then epsilon minus a half, right? So then you get, when you divide them, you get epsilon over 2. But the 2 comes on top here. Okay? All right. And that gives you minus epsilon. So let me draw the picture. So the picture is like this. And this is epsilon. And the intercept went like this. Okay. It hit at x1 equal minus epsilon. Okay? So you overshoot. Then you do it again with x2. I'm not gonna do the same thing. It's different. And you get epsilon. Okay, so he went back to x1. Or sorry, x0. Okay, so the picture is very funny. I mean, I swear, this is beautiful for MATLAB. You will see it just flipping back and forth. So it goes like this, then it goes like this, then it comes back, and then it keeps going, comes back. Is that okay? All right, so Newton's method failed, right? Because f double prime was not bounded. And another problem you will have is you might have Newton's method applying, but it doesn't go to a local min. So I will do an example where it goes to the saddle point. So take x cubed, and the picture of x cubed is something like this. Okay. So at 0, what happens at 0? Is it the other way? Okay, okay. So what happens at 0? Huh? Yeah, but how was that called? We have a word for it from first year. When the f double prime is equal to 6x, right? And what is it called when it goes from negative to positive? Like the concavity changing. Inflection point, thank you. Yeah, so this is the 1D version of saddle point, which is what you said. I just wanted to remember. Okay, good. So I'll do this example. So yeah, you take your derivatives and you start doing Newton's method. Okay, so you get this recursion. Xn plus 1 is equal to a half xn. This is true for all n from 0 to whatever. So you keep solving this and you get contraction, right? So you get xn is a half xn, which is a half xn minus 1, which is 1 over 3, all the way to x0, 2 to the n. So as we take the limit, this guy goes to 0, regardless of what x naught is. Okay? So x star is the saddle point. X star is 0, which is saddle, but it's not local min. Okay? Do you understand? The method gave you the stationary point. It did not give you a local min. Okay? Because no, I should have made the function more. So I could have made it locally like this, and then maybe have a local min. I could have done this, right? So I could have had some local min here. I will find it. I'll do it for you to see it, and then it will still have gone there because Newton's method is local, so it will have hit. Okay, it's whatever. So the point is, Newton's method does not give you local minimums. You wanted the Newton method to fail, but it didn't fail. It should have failed. Newton method should have failed, but didn't, because there is no local min. it goes to minus infinity. Right? Is that okay? Okay, all right. I'll see you. Right, because if you take, right, yes, that's right. It only finds stationary points of that Q of X guy. It doesn't find, yeah, all roots, whatever you want to call it. I mean, right, yes. Yeah, that's what we prove. If what? Yeah, because what was the condition? Yeah, so you have convexity. For what? For what? Oh, I haven't watched. I haven't watched them yet. There's so many. Yeah. Okay, some of them I haven't watched. But other ones